There is a place on Earth called Point Nemo. It sits in the South Pacific, roughly 2,688 kilometers from the nearest scrap of land in any direction. If you stood on a boat at Point Nemo, the closest human beings to you would often be the astronauts on the International Space Station, 400 kilometers above your head. Point Nemo is the loneliest point on the surface of this planet. It has a coordinate. It has a name. We know exactly where it is. But here is what they left out. The cosmos has a Point Nemo too. Somewhere out there, in the deep void between galaxies, there is a single planet that holds the record. A world that was thrown out of its solar system, then thrown out of its galaxy, and is now drifting through intergalactic space at temperatures only a few degrees above absolute zero, with the nearest star tens of millions of light years away in every direction. No telescope on Earth will ever see it. No signal it could ever send would ever arrive anywhere. It is the loneliest planet in the universe. It exists. We just have to figure out where to point. So tonight, slowly, we are going looking for it. Get comfortable. Hit subscribe if you're new here, because by the end of this, the cosmos will have a Point Nemo and a candidate for the loneliest world ever to have existed. Now, let's slowly ease into this. Part 1. A planet that never sees a sunrise. Imagine a world that has never seen a sunrise. Not because of a long polar winter, not because of a thick cloud deck, not because of a brief eclipse. A world that has never, in its entire history, been warmed by the light of a star. A world that has spent every moment of its existence falling through the dark space between suns, with no parent star pulling it into orbit, no morning, no day, no shadow, no warmth from above. The sky above this world is not the sky you know. There is no bright disk moving across it, no slow rotation of dawn into noon into dusk. There is only the faint, distant smear of the galaxy itself, hanging in one direction, and absolute black in every other. And if you stood on the surface of that world, you would have no concept of time. There would be no clock to set by, no shadow to measure, no rhythm of light and dark to lean against. There would only be the slow turning of the planet under a sky that does not change. This is not a science fiction premise. This is a category of object that astronomers have spent the last 15 years confirming exists, in numbers that are quietly reshaping our picture of what a planet is. They are called rogue planets, or free-floating planets, or sometimes just starless worlds. And the most striking thing about them is not how unfamiliar they are, it is how many of them there appear to be. The current best estimate is that the Milky Way galaxy contains more starless planets than it contains stars, possibly several times more. The bright pinpricks of light you see when you look up at the night sky may, it turns out, be the minority of what is actually out there. The real population of the galaxy is what is in between them, invisible, cold, adrift. That is the question this entire video sits on. If most of the planets in the universe never see a sunrise, then almost everything we have ever pictured when we picture a planet a tilted disk orbiting a star, with days and nights and seasons and weather, with continents and oceans and skies, is the rare case. It is the exception. The default condition for a planet in the cosmos, the typical arrangement, the one that statistics now suggest is the most common kind of world out there, is to drift alone through interstellar space, with no star to orbit and no light to see by. That is a strange thing to hold in your mind. It means that the picture you have always carried of the solar system, with 8 planets neatly arranged around a central star, is not a picture of how planets usually live. It is a picture of how a small, privileged minority of planets happen to be arranged. The picture of how most planets live is harder to draw, because most planets live in the dark, where no telescope on Earth can see them. We are inferring them from the briefest, faintest signatures the universe will give us. Flickers of light that last a single afternoon, 25,000 light-years away. Smudges of faint infrared in the depths of a young stellar cluster. The occasional warm point of formation heat in a deep imaging survey. And from those tiny clues, the count keeps going up. So consider, for a moment, what it would actually be like to be on such a world. Take an Earth-sized planet, made of rock and metal, with iron in its core and oceans on its surface, and a thin atmosphere of nitrogen and oxygen. The kind of planet that, if it were orbiting a star at the right distance, could host life. Now ask, what happens to that planet if the star is removed? If the planet is ejected from its solar system in some violent gravitational encounter early in its history and finds itself drifting out into the dark between stars, the surface of that planet would change immediately. The temperature would begin to fall. Within years, the oceans would start to freeze from the top down, then from the shores inward, then all the way through. Within a few thousand years, the atmosphere itself would begin to condense. Nitrogen and oxygen would crystallize into a fine pale frost and fall onto the surface like a slow, silent snow. The sky would empty of weather, then of clouds, then of air. The planet would settle into a hard, still, frozen quiet that would last, in principle, for as long as the universe lasts. There would be no warmth from above. There would be no light from any direction except the faint galaxy in the sky. And yet, even on that world, the story would not be over, because while the surface would die, the interior would not. The planet would still contain the same uranium and thorium and potassium in its core that it contained on the day it was ejected. Those elements would keep decaying. The interior would keep warming itself, very slowly, from radioactive heat, for billions of years. The oceans, several kilometers below a thick crust of ice, might never freeze. The hydrothermal vents on the ocean floor, fed by the planet's own internal heat, might keep running. And the chemistry that those vents support might keep doing what chemistry does when it is given energy and warmth and time, which is, sometimes, to give rise to life. So this is the strange, sleep-friendly fact that this video is built around. Out there, in the dark space between stars, there are billions of planets that no telescope on Earth can see. Some of them are gas giants larger than Jupiter. Some of them are rocky bodies smaller than Mars. Some of them, if the right conditions are met, may have liquid water oceans under their ice. And some of those oceans, possibly, may not be empty. We will almost certainly never confirm any of this. But the math says it is plausible. And the math also says that the universe's default planetary condition is not the lit, sunlit, tilted orbit arrangement that we live in. The default condition is the dark. That is where we are going for the next 2 hours. We are going to walk, slowly, through how the rogue planet category was discovered, why it took so long to find, what we now know about how many of them there are, how they form, what happens to them after they are ejected, and what the most interesting of them might be hiding beneath the ice. We are going to spend time on the freeze, and on the ember beneath the freeze, and on the strange, almost peaceful possibility that the universe's typical planet is a dark, silent, internally warm world that no one will ever visit. And we are going to end at the lonely edge of the picture, with the intergalactic rogues, the planets that have been ejected so violently that they have left their host galaxy entirely and now drift through the empty space between galaxies at temperatures only a few degrees above absolute zero, with nothing in any direction to mark their passage. It is a long, quiet walk. There is no urgency in any of this. The numbers will arrive when they arrive, and the picture will build slowly, the way a picture should when the subject is something we are still in the process of seeing for the first time. Before we leave this opening, hold one more image in mind. Picture the night sky as you usually picture it. The familiar constellations, the bright points of light, the long, pale river of the Milky Way overhead on a clear summer night. That picture is the one every culture in human history has had. It is the picture that astronomers, until about 20 years ago, were also implicitly working with. The picture of a galaxy populated by stars, with planets in tidy orbits around the visible ones. Now, very gently, add the rest. Add the silent crowd in the spaces between the pinpricks. Add the small, dark worlds, all rotating slowly under their own unchanging skies, all warmer at their interiors than at their surfaces, all carrying with them whatever ocean or whatever chemistry they happen to inherit when their parent systems threw them out. Do not add them as a feature, add them as the bulk. The bright pinpricks are the minority of what is in front of you. The real population of the galaxy, the part that does not show up in any photograph, is everywhere between the pinpricks, in numbers that probably exceed the pinpricks themselves. That is the picture this video is built on. The pinpricks are not where the planets are. The planets are between the pinpricks, in the dark. So get comfortable. Find the position you usually find when you settle in. And let us start where the discovery of this entire category started, which was not with a planet at all, but with a flicker of light. Part 2. The accidental discovery. The first hard evidence that the universe was full of starless planets did not come from a planet hunter, and it did not come from someone looking for planets at all. It came from a survey that was set up to do something completely different. It was set up to look for dark matter. In the 1990s and early 2000s, one of the great unsolved problems in astronomy was the question of what the dark matter in the Milky Way actually was. We knew it had to be there because the stars at the outskirts of the galaxy were moving too fast for the visible mass to hold them in. Some kind of invisible material was providing the extra gravity. And one of the ideas that was being seriously considered at the time was that the dark matter might consist of a population of dim, compact objects scattered through the galactic halo, brown dwarfs, maybe, or old neutron stars, or stray black holes, or planet-sized lumps of metal. The general name for this category was MACOs, which stood for Massive Astrophysical Compact Halo Objects. And the way you would detect them, if they existed, was by an effect that Einstein had predicted decades earlier, and that astronomers had only recently figured out how to use as a search tool. The effect was called gravitational microlensing. The idea behind microlensing is simple enough to picture. Light from a distant star travels through space in a straight line until it encounters mass. When it passes close to a massive object, the object's gravity bends the light, the way a glass lens bends light. If you have a foreground mass passing in front of a background star, and the geometry is just right, the gravity of the foreground mass will bend the background light into a small, distorted ring. The ring is too tiny to resolve with any telescope we have, but the total amount of light from the background star, summed up, is briefly larger than it would be if the foreground mass were not there. The star appears to brighten for a while, then dim again as the foreground mass passes out of the line of sight. The duration of the brightening tells you how long it took the lens to cross in front of the star. And the duration is, in a beautiful and direct way, the mass of the lens. A heavy lens has a large Einstein ring and takes a long time to cross. A light lens has a small Einstein ring and crosses in moments. A 30 solar mass black hole, lensing a star deep in the galactic bulge, will brighten the star for about 100 days. A 1 solar mass star will brighten its background for about 25 days. A Jupiter mass planet will brighten its background for about a day. An Earth mass body will brighten its background for about 2 hours. A Mars mass body will brighten its background for less than an hour. The duration is the mass. The shorter the flicker, the smaller the thing that made it. By the late 1990s, astronomers had set up large, dedicated microlensing surveys to look for these brief brightenings. They pointed wide-field telescopes at the densest patches of the sky. They could find the galactic bulge, the bright crowd of stars at the center of the Milky Way, where the density of background stars was so high that you had a reasonable chance of catching a microlensing event in any given night. They watched millions of stars at a time, looking for the brief, characteristic light curves that microlensing produces. And they started finding them. By the early 2000s, hundreds of microlensing events had been logged. The vast majority of them had timescales consistent with stellar masses a few days to a few weeks. The lenses, in other words, were stars. Dim stars, mostly, in the foreground disk of the galaxy, drifting in front of brighter background stars in the bulge. The dark matter hypothesis began to fade. MACOs were ruled out as the explanation for most of the galaxy's dark matter. Microlensing as a tool seemed to have answered its first question. Dark matter was something else, something more exotic. But the surveys were still running. They had been built. They were collecting data. And it occurred to some of the astronomers running them that microlensing might be useful for something other than the original question. It might be useful for finding planets. The way to use it was to look for the very shortest events. The brief flickers, the single-day brightenings, the few-hour brightenings, the events that were too short to be a star and too long to be noise. Each of those, in principle, was the signature of a planet-mass body crossing in front of a background star. If the body was a planet orbiting a foreground star, you would sometimes see a small secondary blip on top of the larger stellar lensing event, and that became one of the standard methods for detecting planets. But if the body was not orbiting any star, if the body was just drifting alone through interstellar space, you would see no stellar component at all. You would see only the short flicker. A clean, brief, isolated brightening of a background star, with no stellar lens around it. That was the signature of a starless world. And in 2011, the moment finally arrived when somebody published the result of looking specifically for that signature. The team was led by Takahiro Sumi at Osaka University, and they were working with the microlensing observations in astrophysics group, the MOA collaboration, using a 1.8-meter telescope at Mount John University Observatory in New Zealand. They had been collecting data for years. They had a sample of 474 microlensing events, drawn from the densest part of the galactic bulge. And when they went through that sample, looking specifically for the short, isolated events that would indicate planet mass lenses with no detectable stellar companion, they found 10 of them. 10 events out of 474 that had Einstein crossing times of about 1 to 2 days, just the right duration for a Jupiter mass body, and, critically, no detectable stellar companion within the geometric reach of the data. That sample of 10 was not large. By the standards of statistical astronomy, it was small, but it was enough to do a calculation. If you assumed that those 10 events were caused by free-floating Jupiter mass planets, and you applied the standard volume and detection efficiency corrections, the implied population was striking. There were, on this analysis, about 1.8 free-floating Jupiter mass planets in the Milky Way for every main sequence star. Nearly twice as many starless Jupiters as suns. The paper was published in Nature. It was titled Unbound, or Distant Planetary Mass Population Detected by Gravitational Microlensing. And it landed with the kind of weight that papers do when they make a number jump by an order of magnitude. Now, the thing to hold in your mind here is what that result felt like at the time. Until that moment, the consensus picture of the Milky Way was the one we all carry a few 100 billion stars, most of them with planetary systems, with the planets in orbit. The Sumi paper said that, in addition to that picture, there was a second, hidden, completely unseen population. A population of giants, drifting alone in the dark, between the stars we already knew about, and there were nearly twice as many of them as the stars themselves. That was the moment the rogue planet category went from a theoretical possibility, an interesting footnote in textbooks, to an empirical fact. The universe had been hiding a category right in front of us, and the only reason we had not seen it before was that there had been no way to look at the things in between the stars. Microlensing was the first tool sensitive enough to catch them, and the first time it was used to look, it caught 10. That number would not, it turned out, hold up exactly as published. There were follow-up surveys still to come, and bigger samples and corrections. The Jupiter mass population would turn out to be smaller than Sumi's first estimate. But the broader population, the existence of a large, hidden, starless, planetary population in the galaxy, would only get more secure as more data came in. The category was real. The only question that remained was how to count it correctly. That recount, when it came, took 6 more years and a much larger telescope. Part 3. The correction. In 2017, a different team published a different paper that quietly turned the Sumi result on its head, without making the population disappear, and in some ways made the larger picture more interesting than the original headline had suggested. The team was led by Przemek Mroz of the Warsaw University Observatory, and they were working with the optical gravitational lensing experiment, the OGLE collaboration, which had been running its own dedicated microlensing survey of the galactic bulge from Las Campanas Observatory in Chile. The OGLE 4 phase of the survey, which ran from about 2010 to 2015, used a 32 detector mosaic camera with a much larger field of view than the MOA survey, and it had been collecting events at a rate that vastly exceeded anything the Sumi team had worked with. By the time Mroz and his collaborators ran their analysis, they had a sample of more than 2,600 microlensing events, roughly 6 times the size of the sample Sumi had used. They looked at that sample with the same question Sumi had asked. How many of these events have the short, isolated timescale of a free-floating Jupiter mass body with no detectable stellar lens? And they found something the Sumi paper had not predicted. They did not find the same excess of 1 to 2 day events. There were short events in the OGLE data, but not at the rate the Sumi result would have implied. When Mroz applied the same volume and detection efficiency corrections, the implied population of free-floating Jupiter mass planets came out, at upper limit to about 0.25 planets per main sequence star, roughly an eighth of the Sumi number. The headline, the one that had said free-floating Jupiters were twice as common as stars, did not survive the larger sample. You might think this would have been the end of the rogue planet story. A surprising paper, then a quieter and more careful paper, then a retraction of the surprise. But that is not what happened. What happened was much more interesting, and it took the field about a year to fully digest it. What Mroz and his team had also found, buried in the OGLE 4 data, was a hint of an excess at the shortest end of the timescale distribution, not at 1 or 2 days. Below that, at a few hours and at less than an hour, the data was sparse at those very short timescales, because most surveys had not been designed to catch events that brief. But there were a few candidates, and the candidates suggested that the real, free-floating planet population peaked not at Jupiter mass, but at lower masses, Neptune masses, super-Earth masses, and below. In other words, the Sumi headline had been pointing at something real. It had pointed at the wrong mass bin. The Jupiter mass column was not where the population lived. The population lived in the smaller masses, which the Sumi sample had not been large enough to resolve. The Mroz paper did not erase the rogue planet category. It moved it. The category got smaller in individual size and probably much larger in number. That picture started getting confirmed almost immediately. In 2020, Mroz and a now broader collaboration that included Andrew Gould and the Korea Microlensing Telescope Network published the discovery that, more than any other single observation, made the small mass rogue planet population tangible. It had a name: OGLE 2016 BLG 1928. The number tells you when and where it was found, a microlensing event toward the galactic bulge in the year 2016. The thing that made this event special was its timescale. Most microlensing events last days or weeks, some last hours. This one lasted 41.5 minutes. From rise to fall, the entire flicker of the background star was over in less time than it takes to make a meal. To put that in context, a Jupiter mass body crossing the line of sight produces an Einstein crossing time of about a day. An Earth mass body produces about 2 hours. To get a 41-minute event, you needed a lens whose mass was below the mass of Earth. The modelling came out to something between a Mars mass body and a small Earth. And critically, when the team looked for any sign of a stellar companion to the lens, they could rule one out to a distance of about 8 astronomical units. There was no star within 8 Earth-Sun distances of the lensing body. Either the lens was a rogue planet, or it was a planet in such a wide and elongated orbit that it was effectively rogue. The strongest reading was a rogue. It was the cleanest single individual case for a terrestrial mass rogue planet anyone had ever published. And it told you something about the scale of what we were finding. The flicker that proved its existence had lasted 41 minutes. A complete signature of an entire world drifting 25,000 light-years away, captured in less time than a sitcom episode. The smallest things, we were now learning, are detected by the briefest events. The shorter the flicker, the smaller the world, and these were the smallest worlds anyone had found so far. Then, in 2023, the picture took another step forward. A team led, once again, by Takahiro Sumi, applied the updated microlensing mass function to the planned bulge survey of NASA's Roman Space Telescope. Roman, when it begins its main mission, will conduct a wide-field infrared microlensing survey that is sensitive to events with much shorter timescales than any previous survey, because it will be in space, above the atmosphere, with a much faster cadence than any ground-based instrument. The team asked, if we use the best current estimate of the rogue planet mass function, including the small mass excess that the OGLE data hinted at, how many rogue planets will Roman detect? The answer was about 400 Earth mass rogue planets across the lifetime of the Roman survey. The previous best estimate had been about 50, an 8-fold increase. The same modelling implied that Earth mass rogue planets in the Milky Way are roughly as common as stars, that for every star you can see in the sky, there is somewhere out there an Earth mass starless world, and that the larger-sized rogues, Neptunes and Jupiters, are somewhat rarer than the small ones. The mass distribution is inverted from what you would expect for stellar formation. Smaller is more common, not less. That inversion is the strange detail in the picture. In normal star formation, smaller masses are also more common. There are far more red dwarfs than there are blue giants, because gravity needs to work less hard to assemble a small object. But the rogue planet mass distribution drops off more steeply than a stellar distribution, and when you compare it to the distribution of planets that orbit stars, the rogue distribution is more bottom-heavy. Smaller worlds dominate, which suggests, very gently, that the formation mechanism is different, that the rogue population is not just the bound population minus the bound part. It is its own thing, with its own preferred mass scale, with its own physics. What that physics is, we will come back to, but hold the result in your mind. The number of starless planets in the Milky Way appears to be at least comparable to the number of stars, and possibly several times larger. The mass distribution favours small bodies, Earth mass, and below. And the only reason we can talk about this at all is that every few weeks, somewhere in the densest part of the bulge, a background star flickers briefly, and the flicker shape tells us what was in front of it. That is the central paradox of rogue planet astronomy. The objects themselves are completely invisible. Their existence is the duration of the flicker. The population that may dominate the planetary content of the entire galaxy is a population we have never directly imaged at high signal-to-noise. We are inferring billions of worlds from a handful of minutes of brightness data 25,000 light-years away. And the picture keeps getting larger. Before we go further into that paradox, though, we should look at the cases where we have not been forced to infer. The cases where the rogue planet was close enough and young enough and still warm enough from its own formation that we could see it directly. There are not many of them, but they exist. And one of them has a name that, by rogue planet standards, has become almost famous. Part 4. The Portrait. The cleanest individual portrait of a rogue planet is a body called PSO J318 5-22. The name comes from the survey that found it the Pan-STARRS 1 survey at Haleakala in Hawaii, and the coordinates of the object in the sky. Pan-STARRS 1 was designed to map the entire visible sky multiple times over, looking for moving objects and brief transients. It was a survey built to catch anything that changed. And in 2010, in the constellation Capricornus, it caught a single point of light that had no parallel in any catalogue of stars. The object was extraordinarily red. It glowed primarily in the infrared, with a peak well outside the visible range and almost no signal in shorter wavelengths. That coloration alone was unusual. Most stars, even cool ones, have at least some optical light. This object was so cool and so reddened by its own atmosphere that it was nearly invisible in any color a human eye can see. Follow-up spectroscopy was done with the NASA Infrared Telescope Facility on Mauna Kea and with the Gemini North Telescope, and the results came back in 2013 in a paper by Michael Liu and colleagues at the Institute for Astronomy in Hawaii. The conclusion, after careful analysis, was that PSO J318 5-22 was not a star. It was not even a brown dwarf. It was a free-floating object with a planetary atmosphere. Its mass was estimated at about 6.5 times the mass of Jupiter. Its surface temperature was about 1,100 Kelvin, hot enough to glow dimly red, but nowhere near hot enough to fuse hydrogen or even deuterium. Its age was estimated at about 12 million years, based on its kinematic membership in the Beta Pictoris moving group, a cluster of young stars and brown dwarfs known to share a common origin in space and motion. The distance came out to about 80 light-years from Earth, practically next door by astronomical standards. What made PSO J318 5-22 so important was not just that it was a rogue planet. It was that, for the first time, an isolated free-floating object had been directly imaged with colors and luminosity that matched the directly imaged young planets like HR 8799b and 2 Mass J 1207b. Those latter objects were known to be planets because they were photographed in orbit around their host stars. PSO J318 5-22 had the same spectral signature, but without the star. It was, in effect, a young, hot, gas giant exoplanet, with no parent system anywhere nearby, drifting on its own through the Beta Pictoris moving group. Let us pause for a moment and imagine standing on it. The planet is 12 million years old. By gas giant standards, that is barely out of infancy. It is still glowing with its own formation heat. The gravitational energy of its initial collapse from the protoplanetary cloud is still leaking out of its interior as infrared radiation. The surface, if you could call it that, is the top of a thick, storm-racked atmosphere of hydrogen and helium, laced with clouds of silicate dust and iron droplets and probably molten metal rain. The upper atmosphere is hot enough to glow a dull, dim red, not bright enough to read by, not even bright enough to see your hand by, but enough that the cloud tops are softly self-illuminated from below. If you could float in those clouds and look up, you would see a sky in two halves. In one direction, the long, pale river of the Milky Way, with the Beta Pictoris moving group's stars scattered through it. In the other direction, nothing at all. Total black. No sun, no source of warmth from above. The only light in the sky is the galaxy itself, and the only heat reaching the cloud tops is the planet's own internal warmth, leaking outward into the cold. There would be no day and no night. The planet rotates, of course, but rotation does not matter when there is no source of directional light. The sky is the same in every direction at every time. The only marker of the planet's spin would be the slow, almost imperceptible shifting of the Milky Way's orientation in the sky, as the planet turned, if you watched for many hours with a clear view. There would be no seasons, no tides driven by a parent star, no equator and no poles, in the sense we use those words on Earth, only a hottest point at the cloud tops directly above the warmest interior column, and the colder points where the planet's outer atmosphere has had a longer time to radiate away. And the most important thing, the thing that makes PSOJ 318, 5-22, a kind of emotional landmark for the rogue planet category, is that we have its portrait. We have its near-infrared spectrum. We have a good measurement of its mass and its age and its distance. We have, in other words, a real specific object, not an inferred statistical population, but a single named world. 80 light-years from Earth, 6.5 times the mass of Jupiter, 12 million years old, glowing softly in the dark with no star to call its own. The first time we put a face on the rogue planet category, this was the face. It is not the only direct-imaged rogue. There have been others. CFBDSIR 2149-04 was found around the same time, also tentatively identified with a young moving group, also estimated to be a rogue planet of a few Jupiter masses. The story of CFBDSIR 2149 is a cautionary one, because the original team later retracted the moving group association. With that retraction, the age constraint collapsed, and without an age, the mass could not be pinned down. The object might be a 4 Jupiter mass rogue planet. It might be a 30 Jupiter mass brown dwarf. It might be billions of years old. It might be hundreds of millions. Without the kinematic anchor of cluster membership, the object floats in classification space the way it floats in physical space, with no nearby reference frame to make sense of it. This is the structural problem of any rogue planet. Without a known formation environment, the age cannot be measured. Without an age, the luminosity cannot be converted to a mass. Rogue planets are, in a real sense, among the hardest individual objects in the sky to characterize, because everything we know about objects elsewhere relies on knowing their neighborhood. There are a few more. SDSSJ 111010 plus 0116, a clumsy name. No shorthand has stuck, was identified in 2015 as a roughly 10 Jupiter mass rogue at about 100 light-years, also linked to the AB Doradus moving group. Then there is WISE 085 5-0714, found in 2014 by Kevin Luhman using data from the WISE infrared survey. WISE 0855 is much closer, at only about 7.25 light-years, the fourth closest system to the Sunday. Its surface temperature is much colder than PSOJ 318 5-22's, about 250 Kelvin, cold enough that water ice clouds have been detected in its atmosphere by the way of follow-up imaging by Faherty and Schema. The mass is somewhere between 3 and 10 Jupiters, and the age is, again, uncertain. And then there is a much more recent one, found in 2025, called CHAR 1000, 107-7626. This is the youngest known free-floating planetary mass object, and the unusual thing about it is that it is actively accreting from a disk. That is to say, it has a protoplanetary disk of its own. A rogue planet with a disk of dust and gas swirling around it, building moons or smaller bodies. That observation, more than almost any other single piece of data, suggests that some rogue planets form in situ from gas cloud fragments, that they are not ejected from stellar systems, but assembled directly out of the interstellar medium, like miniature stars that never reach the size to ignite. The portraits we have are, in other words, a strange mix. Some are clearly young and warm. Some are surprisingly nearby. Some have their own little planetary systems forming around them. None of them look exactly like what astronomers had expected before they started finding them. The category is more diverse than the textbook picture, and the more direct images we get, the more the diversity widens. But while the portraits sharpen the picture for individual objects, they cannot tell you anything about the bulk population. For that, you have to go back to microlensing. And for the bulk population, the most surprising single event was the one that lasted 41 minutes. Part 5. The 41 minutes. Of all the microlensing events that have been published in the last decade, one stands above all the others as the strangest. It has a long, technical name, the kind of name that any rogue planet candidate inherits from the date and field of its discovery. The name is OGLE 2016 BLG 1928. Let us call it 16-19-28 for the sake of conversation, and let us slow down on what actually happened in the data. The event was caught by the OGLE-4 survey camera at Las Campanas in southern Chile in the year 2016. Like every microlensing event, it began as a brief, faint, and unremarkable change in the brightness of a single background star. The background star was deep in the galactic bulge, roughly 25,000 light-years away from Earth, lost in a crowd of millions of similar stars in a tiny patch of sky. The brightening was not large. It was a fraction of a magnitude. To the eye, it would have been invisible. But to the survey, watching that field at high cadence, the brightness change registered. And it registered with a very specific shape. The shape of a microlensing light curve is one of the more elegant signatures in observational astronomy. As the lens crosses in front of the background star, the brightness rises smoothly to a peak, then falls smoothly away. The exact shape, the steepness of the rise, the symmetry around the peak, the duration from start to finish is determined almost entirely by the geometry of the encounter and the mass of the lens. For most events, the rise takes hours. The peak holds for hours or days. The fall takes hours. The full duration of the event is measured in days or weeks. For a heavy lens, it can be measured in months. For 16-19-28, the entire light curve, from the first detectable rise to the final return to baseline, lasted 41.5 minutes. Stop and hold that number for a moment. 41.5 minutes, the time it takes to make a small dinner, the duration of a long phone call, the amount of time it takes to walk a couple of miles. In that span of time, somewhere 25,000 light-years away from Earth, a planet-mass object crossed in front of a distant background star, lensed its light, brightened it, dimmed it, and was gone. The flicker was the entire story. There is no follow-up image of the lens. There never can be one. The lens was too small and too dark to be seen by any direct method we have. The data that proves its existence is a 41-minute brightness curve, beautifully shaped, beautifully clean, with the asymmetry and peak structure of a textbook microlensing event. When the OGLE team and the KMTNet team working together sat down to model the event, the answer they got was striking. The mass of the lens was below the mass of Earth. The best fit was something between the mass of Mars and a small Earth, not a brown dwarf, not a gas giant, a rocky body smaller than the planet you live on, drifting alone in the galactic disk, 25,000 light-years from anyone who could ever observe it. And critically, when they searched the data for any sign that the lens might be a planet in a very wide orbit around a foreground star, they could not find one. Microlensing events caused by bound planets typically have a secondary signature, a small additional blip in the light curve where the host star's gravity also contributes. There was no such signature here. The data could rule out a stellar host within roughly 8 astronomical units of the lens. That is the distance from the Sun to roughly the orbit of Saturn. So, either this lens was a starless rogue planet, or it was a planet in an orbit so wide and so elongated that for all practical purposes it was rogue. Most analyses came down on the rogue side. The paper was published in 2020 in the astrophysical journal Letters. It became the cleanest single individual case for a terrestrial mass rogue planet in the literature, and it changed the conversation. Up to that point, the rogue planet category had been dominated, at least in the public imagination, by the gas giants Jupiter mass and above. 16, 19, 28 pointed downward. The category included Earth mass bodies. It included sub-Earth mass bodies. It included things like Mars and smaller. And those smaller bodies, by every available statistical argument, were more common than the giants. Think about what that means. The smallest planetary worlds, the rocky ones, the ones with the geology and the interiors and the potential for water, those are the most abundant kind of rogue. Earth mass bodies, drifting alone through the galaxy in numbers comparable to the stars themselves. Mars mass bodies, even more numerous than the Earth masses. The galaxy is, on this picture, full of rocky planets in the dark. Many of them are the size and composition of the planet you are listening to this on. There is something almost vertiginous about that. You stand on Earth, in the warmth of a particular yellow star, and the temptation is to think that this arrangement is normal. That rocky planets, of roughly Earth size, with cores and mantles and crusts, are the kind of objects that orbit stars at the right distance. That is the implicit picture in every solar system diagram you ever saw in a school textbook. And then the data comes back, and the data says most rocky planets are not arranged that way at all. Most rocky planets are in the dark. They are not orbiting any star. The configuration you live in, the one you take for granted, is the exception. The statistical norm is a small frozen world with no sun somewhere between the stars. The flicker is the proof. That is the phrase to keep returning to. The smallest things are detected by the briefest events. A planet smaller than Earth, in the dark, 25,000 light-years away, is detected by a single 41-minute brightening of a distant star. There is no other signature. There is no other path to its discovery. There is only the brief, perfectly shaped change in the brightness of something else. The lens, the object itself, is silent. It will never be photographed. It is now lost again in the dark from which it briefly emerged. The OGLE team has logged a handful of other, very short events since then. OGLE-2019 BLG-0551 had a timescale of about a quarter of a day. There are a few more candidates that are not as clean. The statistical pattern, though, is firming up. The shortest events are the most common ones, when you weight by detection efficiency. The mass function of free-floating planets is bottom-heavy. There are more small ones than big ones. The universe has a strong preference, when making things that drift in the dark, for making them small. When NASA's Roman Space Telescope begins its bulge survey later this decade, it will catch these short events at a rate far higher than any ground-based survey can manage, because Roman is in space, above the atmospheric scintillation that obscures the briefest brightenings. The SUMI modeling we mentioned earlier projects roughly 400 Earth mass rogue detections across Roman's lifetime. Each one will be its own 41-minute flicker. Each one will be its own anonymous, unrecoverable, never-to-be-imaged world. By the end of Roman's mission, the rogue planet category will have hundreds of individual entries in a catalogue that will sit beside the bound exoplanet catalogue as a parallel population. The two populations will be roughly comparable in size. The dark population will have arrived as a legitimate, statistically dense, observationally confirmed component of the galaxy, and that is from microlensing alone. Microlensing is a powerful tool, but it is fundamentally a tool for sampling individual bulk flow events in the disk and bulge. It does not give you population pictures of specific stellar nurseries. For the question of how rogue planets cluster together when they are born, and how they relate to their birth environment, you need a different kind of survey. You need to look directly at young stellar clusters with a powerful infrared eye. And that is what the next chapter of the rogue planet story has been about. The next chapter belongs to JWST. Part 6, the JWST chapter. In October of 2023, two astronomers at the European Space Agency, named Samuel Pearson and Mark McCorgrian, released the results of a survey they had been quietly running with the James Webb Space Telescope. The survey was simple in concept. They had pointed JWST's Near-Infrared Camera, NIRCam, at the inner Orion Nebula and the Trapezium cluster. The Trapezium is one of the most photographed regions in all of astronomy. It is a tight group of bright young stars at the heart of the Orion Nebula, about 1,344 light-years away. Most amateur telescopes can pick out the 4 brightest stars of the trapezium on a clear winter night. JWST was looking deeper, with a sensitivity that ground-based telescopes cannot match, in wavelengths that ground-based telescopes mostly cannot see through. They were looking, specifically, for low-mass objects in the cluster, the faintest things the data would tolerate. They found stars, as expected. They found brown dwarfs, also as expected. And they found something nobody was quite prepared for. They found more than 500 isolated, planetary mass objects in the surveyed region. Bodies with masses estimated between roughly 0.6 and 14 Jupiter masses scattered through the cluster, with no parent star anywhere nearby. The objects were young, about 1 million years old, consistent with the age of the trapezium itself, and they were still glowing with the formation heat that JWST's infrared eye is uniquely suited to detect. Each one was a free-floating planetary mass object in a single, well-mapped, young stellar nursery, in numbers that no previous survey had ever found. That was the first surprise. The second surprise, the one that became the headline and that has dominated the debate ever since, was the binary fraction. Of those more than 500 free-floating planetary mass objects, 42 of them appeared in gravitationally bound pairs. 2 free-floating planets, orbiting each other, with no star between them. Pearson and McCorgrian gave them a name. They called them JUMBOs, which stood for Jupiter Mass Binary Objects. 42 JUMBOs in a single survey of a single young cluster, a binary fraction of about 8% of the free-floating planetary population. For some reason, that number, 8%, became the part of the result that broke a lot of people's models. The reason has to do with how rogue planets are supposed to form. The standard explanation, the one that had dominated the field for decades, was that rogue planets were ejected. They formed in stellar systems, in the disks of gas and dust around young stars, the same way ordinary planets form. Then, At some point in the first few 100 million years of the system's life, gravitational instability launched them out. Maybe a larger planet's gravity perturbed a smaller one onto an escape trajectory. Maybe a passing star ripped one out. Maybe the host star itself died in a supernova and the asymmetric explosion ejected the surviving worlds. Whatever the mechanism, the ejected planet would leave alone. It would carry away its own ejection velocity. It would travel through space as an isolated object with no companion. The trouble with that picture, when you applied it to the jumbos, was that producing a bound binary of two planet mass bodies from an ejection event is extraordinarily hard. The two planets have to escape together. Their relative velocity at the end of the ejection has to be small enough that they can stay gravitationally bound to each other afterwards. The gravitational energy of their mutual binding is tiny Jupiter mass bodies bind very weakly to each other at planetary separations, and any significant kick will pull them apart. To produce 42 bound pairs in a single cluster, by ejection, you would need the ejection events to be improbably gentle, improbably symmetric, and improbably common. The numerical simulations did not produce them. Several groups have tried. The N-body codes, when fed realistic stellar systems and asked to eject planet mass bodies, almost never produce bound planetary binaries as a byproduct. The expected output is single rogues, not pairs. So, either the simulations were missing some critical physics, or the jumbos were not ejected at all. They had formed some other way. And the leading candidate for that other way was direct collapse from gas cloud fragments. The idea is this. In a turbulent star-forming region like the Orion Nebula, gas is constantly being compressed and decompressed by shocks and instabilities. Some of those compressed regions become dense enough to collapse under their own gravity. If a collapsing region happens to have enough mass to ignite hydrogen fusion, you get a star. If it has enough mass to fuse deuterium, but not hydrogen, you get a brown dwarf. If it has less mass than the deuterium fusion threshold, which is about 13 Jupiter masses, you get something below the brown dwarf line, a sub-brown dwarf, a free-floating planetary mass object. And if the turbulent collapse happens to produce two such fragments in the same pocket, gravitationally close to each other, the two fragments might bind into a jumbo. This is, in some ways, an unsettling result. It blurs the boundary between stars and planets in a way that the field had not fully come to terms with. The standard textbook picture had it that stars formed by gas cloud collapse and planets formed by accretion in protoplanetary disks. The two processes were different. Stars came from the top down, from a cloud collapsing into a single body. Planets came from the bottom up, from dust grains in a disk slowly building into larger and larger bodies. The jumbos, if they really formed by direct collapse, are planets in the planet mass range, but stars in the formation pathway. They are something the textbook category system did not have a clean name for. The result has been challenged. In 2024, several theoretical groups began publishing simulations, suggesting that some of the candidate jumbos might not be truly planetary mass, and that the JWST imaging cannot, on its own, distinguish a 1 Jupiter mass object from a low-mass brown dwarf without spectroscopic confirmation. There has been pushback on the entire jumbo interpretation. Some authors have argued that the candidates are real, but the formation explanation is wrong. Others have argued that the candidate count is overestimated. The debate is ongoing. In 2024, a radio telescope follow-up using the E. Merlin array in the United Kingdom confirmed several of the candidate jumbo sources independently in radio emission. The probability that the infrared and radio signatures of those sources were coming from independent objects was estimated at about 1 in 10,000. The sources are physically real. Whether they are planet mass is a separate question, and that is what spectroscopic follow-up with JWST's near-infrared spectrometer, is being used to investigate now. Whatever the exact resolution turns out to be, the broader result stands. The trapezium cluster contains a population of free-floating planetary mass objects far larger than any previous survey had detected. Some of them, possibly many of them, are in bound pairs, and those bound pairs are difficult to produce by ejection, which suggests that at least part of the rogue planet population in the galaxy forms not by ejection from a stellar system, but by direct collapse of a cloud fragment that never quite became a star. So put the picture together. The microlensing data tells you the bulk. The galaxy contains a vast, hidden, predominantly low-mass population of rogue planets, possibly outnumbering the stars themselves. The direct imaging data tells you what the individual portraits look like. Nearby, young rogues like PSOJ 318, 5 to 22, still warm, with formation heat. The cluster surveys with JWST tell you about the formation. At least some of the population is born starless, assembled directly from collapsing gas pockets that never reach the size to ignite, sometimes even in bound pairs. 3 independent lines of evidence, 3 different mass regimes, 3 different formation environments, all converging on the same large-scale conclusion. The category of starless planet is real, it is abundant, and it is more diverse than anyone had expected. That convergence is what makes the rogue planet population a settled topic now, rather than a speculative one. It is also why the natural next question is one that the early papers did not have to engage with. Now that we are sure these worlds exist, in numbers comparable to the stars, the next question is how they got there. How does a planet end up in the dark? Part 7. How a planet loses a star. A planet that begins life in orbit around a star can lose that star in a few different ways. Each one has a distinct signature. Each one writes a slightly different story onto the resulting rogue. Let us walk through them in order of how common they appear to be. The most likely cause of planetary ejection, by a comfortable margin, is what astronomers call planet-planet scattering. The setup is this. A young planetary system, only a few million to a few 100 million years old, is rarely the calm, stable arrangement we see in mature systems like our own solar system. Young systems are chaotic. They have more planets than they will eventually retain. Those planets are still settling into their long-term orbits. They cross each other's paths. They tug on each other's trajectories. Over millions of years, the cumulative effect of those mutual perturbations builds up. At some point, often when a particularly heavy planet, a Jupiter-class body, finds itself in a resonant relationship with a neighbor, the system tips into instability. Orbits cross. Close encounters happen, and in the close encounters, gravitational kicks can be powerful enough to launch one of the planets onto a hyperbolic trajectory, an escape trajectory. The planet sails outward, never to return. That is the standard mechanism, and it is, by all current modeling, the dominant ejection pathway for the rogue planet population. Most planetary systems are unstable enough, early enough in their lives, to eject at least one of their members. Some estimates suggest that perhaps half of all planets that ever form in stellar systems end up unbound. The visible solar systems we study, including our own, are the survivors of this culling. The 7 planets we see arranged around the Sun today are the ones that did not get kicked out. There may have been 8 or 9 or 10 in the deep past, and 1 or 2 of them may now be drifting in the dark somewhere in the galactic disk, having been launched out of the early solar system by one of the gas giants. We have no way to know. The kick velocity from planet-planet scattering is typically a few kilometers per second to about 10 kilometers per second. That is the rough escape velocity of the host star's gravitational well at the radius where the ejection took place. The ejected planet inherits that velocity and drifts outward. It will spend the rest of its existence moving relative to the local frame of nearby stars at that speed. That is fast, by human standards. A jet airliner cruises at about 1/4 kilometer per second. The Voyager spacecraft, after 50 years of gravitational assists and rocket boosts, are moving at about 17 kilometers per second relative to the Sunday. An ejected rogue planet moves at roughly the same speeds, in a random direction with nothing to slow it down. It will cross the galaxy in time spans of order 100 million years to a few billion years, depending on its trajectory. The second mechanism is what astronomers call stellar flyby. The setup is similar to planet-planet scattering, but the disrupting force comes from outside the system rather than from inside. A passing star, drifting through the same patch of the galaxy, comes close enough to a planetary system to perturb the orbits of the planets. If it comes close enough, within a few hundred astronomical units, say the gravitational pull of the passing star is comparable to or greater than the pull of the host star at the outer reaches of the planetary system, the outer planets are pulled outward. Some are stripped away entirely, captured by the passing star, or thrown into interstellar space on hyperbolic trajectories. Stellar flyby ejections are most common in dense stellar environments, especially in young clusters where the stellar density is much higher than the average galactic density. Young clusters like the trapezium, where the jumbos were found, are dynamically active places. Stars are still moving relative to each other at significant fractions of the cluster's escape velocity. Close stellar encounters happen on million-year timescales. Planetary systems in those clusters are vulnerable. Many of the rogue planets that end up in the galactic disk may have originated from stellar systems in dense clusters that were broken up in the first 100 million years of their existence. Flyby ejections produce higher velocities than planet-planet scattering, because the kinetic energy of the passing star contributes. The ejection velocity dispersion from binary flybys is about 3 times larger than the dispersion from internal scattering. So a rogue planet, ejected by a stellar flyby, tends to be moving faster than one ejected by planet-planet scattering. The velocity distribution is one of the clues astronomers use when they catch a rogue in a microlensing event to try to infer its origin. The third mechanism is the supernova. A sufficiently distant planet can survive the death of its host star. The shock wave passes over it, but the planet is far enough away that its surface is not entirely vaporized. After the supernova, however, the host star is gone. Its mass has been blown away, much of it in an asymmetric burst. The planet's orbit, which depended on the host star's gravity, is suddenly altered. The remaining stellar remnant, a neutron star or a black hole, has only a fraction of the original mass and is often moving rapidly away from the original location of the star, having received its own kick from the asymmetric explosion. The planet finds itself in a system that no longer exists. Sometimes it ends up bound to the remnant. More often, especially for the outer planets, the supernova kick is sufficient to unbind it, and the planet sails away on an escape trajectory. Supernova-ejected planets tend to have very high velocities, sometimes a few hundred kilometers per second. They are a small fraction of the total rogue population. Supernovae are not common, and most stars do not produce them. But they exist, and they form a high-velocity tail in the rogue planet population. The fourth mechanism is the one we mentioned in connection with the jumbos, direct formation without ever having a parent star. This is not really an ejection mechanism because nothing is being ejected, but it is one of the pathways by which planet mass bodies end up unbound. A cloud fragment in a star-forming region collapses to make a substellar object that is too small to ignite hydrogen or even deuterium. The result is a planet made by the star formation process that never had a star. It is, in formation pathway, more akin to a brown dwarf than to a traditional planet. But by mass, it falls in the planetary range, and it is starless from birth. The fraction of the rogue population that formed by direct collapse versus the fraction that formed by ejection is not yet settled. The JWST cluster surveys suggest that direct collapse contributes a significant fraction in young clusters. The microlensing data suggests that ejection contributes a significant fraction in the older mixed disk population. The two mechanisms together produce the full population we observe. The mass distribution of each is different. Direct collapse appears to favor the higher mass end. Ejection appears to favor the lower mass end. The combination produces the bottom-heavy mass function the microlensing surveys are seeing. There is a final point worth making about all of this. In our own solar system, the kind of dynamical chaos that ejects planets was almost certainly active in the first few 100 million years. The current arrangement of the 8 planets Mercury, Venus, Earth, Mars in the inner system, then Jupiter, Saturn, Uranus, Neptune in the outer system, is stable now, but it was not always so. Models of early solar system dynamics, particularly the Nice model and its successors, suggest that the giant planets migrated significantly in the first 500 million years. Some models predict that the early solar system had a 5th giant planet, sometimes called Planet 9 in the older literature, though the term has now been reused for a different hypothetical object, which was ejected during the dynamical reshuffling. If that model is right, then there is a planet mass object out there in the galaxy right now, drifting through interstellar space, that used to orbit our own Sunday. It would have been ejected about 4 billion years ago. It would have crossed roughly 400,000 light-years of interstellar distance since then, many times the diameter of the Milky Way's stellar disk. It would, if it still exists, be unrecognizable from any external observation. That is not a fanciful claim. It is the standard implication of mainstream solar system formation models. The visible solar system is the survivor. There may have been a sibling planet, ejected in the first 500 million years, now lost in the dark. We will never find it. And it is one of, by current count, perhaps several 100 billion rogue planets in the Milky Way. The galaxy is, on this picture, full of orphans. Once a planet is in the dark, the next question is what happens to it. The interior of a planet is, on geological timescales, surprisingly slow to cool, but the surface is a different story. Part 8. The Freeze. So take a planet, an Earth-mass rocky body, with continents and oceans, and a thin atmosphere of nitrogen and oxygen, and a little water vapor, and a trace of carbon dioxide. The kind of planet that, if it were orbiting a yellow main-sequence star at the right distance, could host a biosphere. Now imagine that planet is ejected from its solar system by a close encounter with a gas giant. The gravitational kick gives it about 5 kilometers per second of velocity in some random direction relative to the host star. It sails outward, picking up speed slightly as it falls down the gravitational well of the rest of the galaxy, and within a few 100,000 years it has crossed the heliopause of its parent system and entered interstellar space. The host star recedes into the distance, becoming first dim, then a bright point of light, then indistinguishable from the other stars in the sky. After 1 million years, there is no way for an observer on the surface to identify which star was the parent. The planet is alone. What happens to the surface during that 1 million years? The dominant change is temperature. While the planet was in orbit, the surface was warmed by the host star to whatever the orbit allowed, say, an average of about 288 Kelvin, the average surface temperature of Earth. After ejection, the star's heat flux drops away as roughly the inverse square of the distance, and within a few 100 years, the contribution of the host star to the planet's energy budget has become negligible. The only energy source remaining is the planet's interior heat. For an Earth mass body, the interior heat flux at the surface is about 0.08 7 watts per square meter on average. Compare that to the roughly 1,360 watts per square meter that the sun delivers to the top of Earth's atmosphere on the day side, and you see the imbalance. Without the sun, the surface has to radiate away most of what it had, and the new equilibrium temperature is much, much lower. The new equilibrium for an Earth mass rogue, with only its internal heat flux balancing radiation loss, comes out to about 37 Kelvin. That is 40 degrees above absolute zero. It is cold enough that nitrogen, the dominant component of Earth's atmosphere, condenses out of the gas phase and falls as a fine, pale snow onto the surface. Oxygen does the same. Argon does the same. The atmosphere itself, the gaseous envelope that supports weather and pressure and breath, settles onto the surface over the course of a few thousand to a few tens of thousands of years, transforming gradually into a thin layer of frozen air on top of the ground. The oceans take longer because water has a high latent heat of fusion and because the deep oceans contain a lot of stored heat that takes time to radiate away. But they freeze. They start at the surface, where the cooling is fastest. A thin layer of sea ice forms first, then thickens. The thickening accelerates as the wind dies down without solar heating to drive atmospheric circulation. The wind dies within a few thousand years, and the ice grows downward into the water column. After about 10,000 years, the surface of every ocean is covered by a thick ice cap, several hundred meters deep. After 1 million years, the ice cap has grown to several kilometers thick, with liquid water remaining only at the deepest part of the ocean basins, where the interior heat from below is sufficient to hold off the cold from above. Let me slow down here, because this is the moment that holds the emotional weight of the entire video. Stand on the surface of a small terrestrial rogue planet during the first 1 million years after ejection. The atmosphere is thinning. You can hear it thinning, or rather you can hear sound itself getting fainter, because the pressure is dropping and sound needs a medium to travel through. Wind that used to rustle leaves now barely moves dust. Then the wind stops entirely, because the air has settled onto the ground. The leaves, if there were any, are dead. The trees, if there were any, are frozen solid down to the roots. The oceans, which used to be blue, are turning from blue to white as the surface ice thickens. The shoreline, which used to move with the tide, is fixed. There are no tides without a moon's gravity dominating the water, and even with a moon, the energy that drove the tide cycle came mostly from the sun's heating of the atmosphere. Without the sun, the tides die. The sky is the strangest part. You look up, and there is no Sunday, there is no parent star anywhere you cannot identify it. There is no moon, or if there is a moon, it is dim and only barely visible, illuminated only by the same faint galactic light that lights the planet. There are no clouds, because there is no water vapor in the air. There are no auroras, because there is no solar wind. There is only the long pale river of the Milky Way in one part of the sky, and absolute black in the rest. The galaxy itself becomes the only feature of the night, and there is no day to contrast it against. The light from the galaxy is too faint to read by, too faint to see your hand by. It is enough, on a clear stretch, to give you a sense of which direction is up. That is all. You would be cold, catastrophically cold. The surface temperature, settling toward 37 Kelvin, is colder than any natural environment on Earth. It is colder than the upper layers of Saturn's moon Enceladus. It is colder than the surface of Pluto. It is, in many parts of the planet, colder than the boiling point of liquid nitrogen. The atmospheric snow on the ground would not melt under your boots. It would not even warm. The water ice cap on the oceans would be harder than concrete. The rock itself, if you could see it through the frost, would be brittle. The world would be a single, hard, still, frozen quiet that would last in principle for as long as the planet held together as a planet, which is to say, for billions of years. This is the freeze. It is what happens to every Earth-like rogue planet within a few million years of ejection. The surface biosphere, if there was one, is gone. The oceans are frozen down to depths where the interior heat from below begins to balance the cold from above. Above that depth, everything is ice. Above the ice, everything is frost. Above the frost, the sky is black, and the planet just sits like that, forever, or for as long as the universe lets it. It drifts through the galactic disk at 5 or 10 kilometers per second, relative to the local stars, slowly making its long, quiet circuit around the center of the Milky Way, passing through molecular clouds and star-forming regions and empty interarm gaps, with no awareness of any of it. Its surface tells no story to anyone watching. Its atmosphere is on the ground. Its oceans are frozen solid in their basins. Its weather, in the human sense, has ended. The world is a small dark sphere in the dark, indistinguishable from any external observation, from any other small dark sphere in the dark. That is the brutal version of the rogue planet story. It is the version that emphasizes loss. The loss of the parent star, the loss of the atmosphere, the loss of the oceans, the loss of any possibility of surface life. From a thermal and atmospheric perspective, the freeze really is a kind of ending. The surface chapter of the planet's life is over. But that is not the full story. Because while the surface freezes, the interior does not. The interior holds its heat. And the interior, on a long enough timeline, is where the next chapter quietly opens. Beneath the kilometers of ice that form the new outer crust, in some cases, there is still liquid water. In some cases, there is still chemistry, and in some cases, there may still be something else. Something the surface gave up, but that the depths did not. The ember beneath the ice is the part of the rogue planet story that is hardest to ignore. Part 9. The Ember Beneath the Ice. In 1999, a planetary scientist at Caltech named David Stevenson published a short paper in the journal Nature with a strange and quiet conclusion. The paper was titled Life-Sustaining Planets in Interstellar Space, and its argument was simple. It was possible, Stevenson argued, for a rogue planet to keep liquid water on or near its surface for billions of years, even with no host star, if certain conditions were met. The key condition was a thick atmosphere of molecular hydrogen. Hydrogen, of all atmospheric gases, has an unusual far-infrared spectroscopic property. At sufficient pressure, the hydrogen molecules collide with each other often enough that pressure broadening of their absorption bands becomes important. The hydrogen atmosphere becomes a powerful greenhouse, opaque to outgoing infrared radiation in a way that no thin atmosphere can match. If a rogue planet had retained a hydrogen atmosphere of perhaps 10 to 100 bars of pressure from its early formation, the modest interior heat flux of the planet would be trapped efficiently enough to keep the surface liquid. Water could pool on the ground. The planet, ejected from its solar system and drifting through interstellar space at no fixed temperature, would still have a habitable surface, lit only by the planet's own dim infrared glow, with liquid water ponds and seas, indefinitely. That picture became known, informally, as a Stevenson planet. It is a specific kind of rogue. It would have to be a body massive enough to have retained its hydrogen envelope through the early gas dispersal phase of its parent stellar system. Earth's gravity is not quite strong enough to hold hydrogen against thermal escape over billions of years. A Stevenson planet would have to be larger, at least several Earth masses, probably more. And it would have to have escaped its parent system before the hydrogen envelope was stripped by the host star's stellar wind. The conditions are demanding, but they are not impossible. The model predicts that some fraction of rogue planets, somewhere in the galaxy, are in this state right now. Warm, liquid-surfaced, lit by their own interior glow, drifting through the dark. In 2011, Dorian Abbott and Eric Switzer at the University of Chicago published a follow-up paper that extended the Stevenson idea in an important way. Their model, which they called the Steppenwolf model, considered a different kind of rogue planet. Not one with a hydrogen atmosphere, but one with a thick water ice cap over a subsurface ocean. The idea was that an Earth-mass rogue planet with terrestrial geochemistry would freeze solid on the surface, but could maintain a liquid subsurface ocean for billions of years if the ice cap was thick enough to insulate the underlying water from the cold sky. The ice would act as a kind of thermal blanket. The interior heat from radioactive decay would be trapped beneath the ice. The ocean below would remain liquid, perhaps as much as several kilometers deep, kept warm by the same radiogenic heating that powers Earth's geothermal flux. The Steppenwolf model gave the ice cap a thickness of a few kilometers and predicted that the underlying ocean could persist for as long as the radioactive heat sources held out, which is several billion years. This is more than a theoretical curiosity. We have direct evidence that subsurface oceans of this kind exist in our own solar system, on bodies that do orbit the Sun but are too far away to receive much of its heat. Europa, the second of the 4 Galilean moons of Jupiter, has an ice cap several kilometers thick over a global ocean of liquid salt water that contains roughly twice the volume of all Earth's surface oceans combined. The ocean is kept liquid not by radiogenic heat, but by tidal flexing. Jupiter's gravity stretches and squeezes Europa as the moon orbits, and the friction from that flexing dissipates energy as heat in the interior. Enceladus, a small moon of Saturn, does the same thing on a smaller scale. Its subsurface ocean has been confirmed by the Cassini spacecraft's measurements of the geyser plumes that erupt from its south polar region. Plumes that contain organic molecules and silica particles consistent with active hydrothermal venting at the ocean floor. Titan, also a moon of Saturn, has a subsurface water ocean beneath its hydrocarbon-rich surface. Ganymede, Callisto, and probably Pluto and Triton and Ceres all have subsurface liquid water layers of some kind. These subsurface ocean worlds are, in the solar system, the rule rather than the exception for outer system bodies. They are kept liquid by various combinations of tidal heating, radiogenic heating, and pressure effects. None of them are starless. They all orbit the Sun, even if at distances where the Sun's direct heating is negligible. But the physics that keeps their oceans liquid would work just as well on a rogue planet where the Sun is absent altogether. The interior heat does not know whether there is a star outside. It just heats. And as long as there is an ice cap thick enough to keep the cold sky from drawing the heat out faster than the interior can supply it, the liquid layer persists. Let us now move below the ice. Take that small, terrestrial rogue planet from the freeze passage. Move 3 kilometers below its surface. You are now under a hard ice ceiling, several kilometers thick, dark and silent and motionless. Above the ice, the surface is at 37 Kelvin. Below the ice, the water is at about 4 degrees Celsius at the ocean floor, dropping toward 1 degree near the ceiling, the same temperature gradient you would find at the bottom of an ice-covered lake on Earth. The ocean is not warm, but it is liquid. It is dark. There is no light of any kind. There is no surface chemistry, no photosynthesis, no oxygen production from above, no nutrient flux from runoff. There is only the water and the rock at the bottom and whatever chemistry is happening at the boundary between them. The chemistry at that boundary, on Earth, is not trivial. The mid-ocean ridges of our planet are sites of intense geological activity. Hydrothermal vents, black smokers and white smokers, push superheated, mineral-rich water out of the rock into the ocean. Around those vents, in temperatures ranging from a few degrees Celsius up to over 100 degrees Celsius, entire ecosystems thrive without any input from sunlight. The discovery of these ecosystems, beginning with the Galapagos Rift in 1977, was a revolution in biology. It turned out that life did not need the Sunday. Life could run perfectly well on chemical energy from the planet's interior. The vent ecosystems include tube worms, 2 meters long, vast colonies of vent mussels and shrimp, fields of bacterial mats, and an entire metabolic kingdom of chemosynthetic archaea that derive their energy from the oxidation of hydrogen sulfide and methane and hydrogen. The total biomass of Earth's deep-sea vent ecosystems is large. It is comparable, by some estimates, to the biomass of all surface ecosystems combined. The vents are not marginal habitats. They are alternative biospheres, running in parallel with the photosynthetic biosphere we are more familiar with, completely independent of the Sunday now transfer that picture to a rogue planet. The surface is dead. The atmosphere is frozen on the ground. The sky is black. But 3 kilometers down, under the ice, there is a liquid ocean. At the bottom of that ocean, where the planet's rocky mantle meets the water, the planet's interior heat is leaking outward at the same rate it does on Earth. If the planet has the right mineralogy basaltic ocean floor, fresh crustal rock, some sulfur and iron and carbon in its bulk composition, then there will be hydrothermal venting at the boundary. The vents will spew mineral-rich water into the dark, and the chemistry that builds around those vents will be the same chemistry that built the first ecosystems on Earth. If life had already arisen on the planet before ejection, life around those vents would survive the ejection. The surface biosphere would die, but the vent ecosystems would carry on, indifferent to the loss of the Sunday. They were never using the sun anyway. They were using the planet's own heat, and the planet's own heat has not gone away. If life had not yet arisen on the planet before ejection, the conditions at the vents are exactly the conditions that some researchers, Michael Russell, William Martin, Mike Wadhams, and others have argued were the actual cradle of life on Earth. The iron-sulfur clusters that catalyze the most fundamental enzymes in living cells today have the same structure as the inorganic iron-sulfur minerals that precipitate at hydrothermal vents. The proton gradients across the porous mineral structures of submarine alkaline vents look mechanistically very similar to the proton gradients across cell membranes that drive ATP synthesis in every living cell on Earth. The case is not closed, but it is serious. Life may have begun at vents like these, and vents like these may exist right now beneath the ice of an unknown number of rogue planets drifting through the galaxy. That is the ember beneath the ice. It is the realization that loss of a star is not loss of life. The surface chapter ends. The dark chapter, the warm in the dark chapter, may keep running. For as long as the planet's interior holds heat, which is to say, for billions of years the ocean under the ice can stay liquid. And if there is life in that ocean, or if life can arise in it, the loss of the parent star is a footnote in the planet's history, not the end of it. That is the optimistic version of the rogue planet story. It is the version that emphasizes persistence. We will not know which rogue planets have it. We will likely never confirm a subsurface biosphere on any of them, because the ice cap that keeps the ocean liquid also makes the ocean undetectable from outside. But the math says it is plausible. And the math says that, in a galaxy with hundreds of billions of rogue planets, plausibility on a per-planet basis becomes inevitability somewhere. Part 10. Could life arise here? There is a separate, harder question lurking under the subsurface ocean idea. It is not the question of whether existing life can survive on a rogue planet. That is the version we have just walked through, and the answer, in principle, is yes for any vent ecosystem with a deep enough ice cap. The harder question is whether life can begin on a rogue planet, whether the chemistry that originated life on Earth could originate it again independently on a starless world that never had a parent system in the first place. The reason the question is harder is that origin of life chemistry is, even in the best case, fragile. It requires very specific conditions. It probably requires liquid water. It probably requires a source of free energy that can drive reactions away from equilibrium. It probably requires a substrate of some kind, a way to concentrate molecules so that the right ones meet often enough to react. It probably requires a flux of organic precursors, like amino acids and nucleotide bases and lipid molecules, and it probably requires time, a lot of it. Most origin of life scenarios on Earth assume some combination of solar input, UV photochemistry, for example, atmospheric chemistry, surface ponds drying and re-wetting, lightning, and impact delivery of organics from comets. On a rogue planet, most of those mechanisms are unavailable. There is no solar input. The atmosphere is on the ground as frost. The surface is solid ice all the way down. There is no lightning because there is no atmosphere to ionize, and no convection to drive charge separation. The only mechanism that survives is the impact delivery, and even that is sporadic. What does survive, abundantly, is the vent chemistry. Submarine hydrothermal vents do not need sunlight, atmosphere, ponds, or lightning. They run on the planet's own interior heat and on the geochemistry of fresh crustal rock meeting water. They produce free energy in the form of strong redox gradients across mineral barriers. They concentrate molecules in their porous mineral structures. They generate organic precursors through the abiotic chemistry of carbon dioxide reduction. They produce iron-sulfur clusters that look very much like the active sites of modern enzymes. The case that life on Earth began at vents is not proven, but it is one of the leading hypotheses, and it is supported by the deep similarity between vent geochemistry and the most ancient enzymatic machinery. If life on Earth did begin at vents, then there is no reason in principle that life could not also begin at vents on a rogue planet. The vents themselves do not need to know whether they are on a world that orbits a star. They operate the same way either way. The same iron-sulfur chemistry, the same proton gradients, the same slow turnover of organic precursors. Give the chemistry enough time, give the vent system enough volume, and the same statistical processes that led to the first replicating cells on Earth could lead to them somewhere else. The constraint is time. On Earth, life seems to have appeared within a few 100 million years of the planet's formation. That is fast, on a geological scale. It may be that origin of life chemistry is rapid given the right conditions, or it may be that we are simply seeing the lucky outcome on a planet where many independent origin events could have occurred and at least one took hold. Either way, the timescale on Earth is short. A rogue planet drifting through the galaxy for several billion years with active vent systems would have plenty of time. If the chemistry works on a per-planet basis, with even a modest probability, it should work on some rogue planets somewhere. The author, Avi Loeb, and his colleague Manasvi Lingam, in a series of papers in 2017 and 2018, took this idea further. They calculated that, if rogue planets with subsurface oceans support biospheres at any reasonable frequency, the total habitable volume of liquid water in interstellar space exceeds the total habitable volume of all the surface oceans on all the exoplanets orbiting stars in their habitable zones by orders of magnitude. There is simply more water, in more places, beneath the ice of rogue worlds than on the surfaces of Earth-like exoplanets, because there are so many more rogue worlds. That is a striking inversion. We have been searching for extraterrestrial life almost exclusively at the lit places, the Goldilocks zones around stars, the narrow bands of orbital radius where stellar input keeps surface water liquid. SETI, the Drake equation, the Kepler mission, the radial velocity exoplanet surveys, all of them have been built around the assumption that life would be where the starlight is. The Lingam-Loeb calculation suggests that this assumption may have been the wrong way to look. If life follows water, and water follows internal heat, and internal heat is more abundant in rogue planet interiors than in star-warmed exoplanet surfaces, then the bulk of the cosmic biosphere may be in the dark. We will not be able to test that. We have no way to image the interior of a subsurface ocean rogue planet. We have no way to send a probe to one. The nearest known rogue planet, Y0855, is 7.25 light-years away, which means a flyby mission at current technology would take over 100,000 years to arrive. Even if we built faster spacecraft, the science return from a single flyby past a frozen, atmosphere, on-the-ground world would be minimal. The interior would remain unprobed. The ocean, if it exists, would remain hypothetical. The biology, if it exists, would remain entirely a matter of inference. But the math is the math. If there are hundreds of billions of rogue planets, and if even a small fraction of them, say 1 in 10,000, have the right conditions for subsurface oceans, then there are tens of millions of subsurface ocean worlds in the Milky Way alone. If even a small fraction of those, say 1 in 1,000, have active origin of life chemistry at their vents, then there are tens of thousands of independent origins of life happening right now in the dark. We cannot see any of them, but the math says they should be there. This is the strange, quiet possibility that the rogue planet category opens. It is not the dramatic alien civilization possibility. There is no plausible mechanism by which a rogue planet biosphere, trapped beneath kilometers of ice with no atmosphere and no sky, could ever evolve a technological civilization. The vent ecosystems on Earth, after billions of years of evolution, are still microbial and metazoan, never reaching anything like the complexity of surface ecosystems. The constraints are too severe. The energy budgets are too tight. The metabolic options are too narrow. A rogue planet biosphere, even at its most successful, would probably be microbial all the way down. It would not build telescopes. It would not send signals. It would not know that it is on a rogue planet, or that there is a galaxy outside the ice. But it would be alive, and it would be there. In numbers that, if the math is even approximately right, dwarf the population of all sun-warmed surface biospheres in the galaxy combined, the bulk of cosmic life, if life is anything like what the optimistic models suggest, lives in the dark. The lit biospheres on planets like Earth, where photosynthesis runs in the open and ecosystems can complexify all the way up to creatures that build microscopes and ask questions about rogue planets, are the rare exception. The default biosphere, the median biosphere, the one that statistics predict is the most common kind in the universe, is small and microbial and frozen over and entirely unaware of what is outside its world. That is, in some ways, the gentlest reframe in the entire video. The most common kind of planet may be starless. The most common kind of biosphere, if biospheres are anything like Earth's, may be subsurface. And the rare, sunlit, sky-watching arrangement we live in, the one that makes us assume the cosmos must be full of bright worlds and bright minds that may turn out to be the unusual case. Not the typical one. We will sit with that for a moment, and then we will go to the loneliest version of the story, the rogue planet that was thrown not just out of its solar system, but out of its galaxy entirely. Part 11. Out of the Galaxy. The galactic escape velocity at the orbital radius of the Sun is about 550 kilometers per second. That is the speed at which an object, moving outward from the Milky Way's center at that radius, has just enough kinetic energy to escape the galaxy's gravitational pull and never fall back. Anything moving slower will eventually be turned around by the galaxy's mass and pulled back. Anything moving faster will leave forever. 550 kilometers per second is very fast. It is about 30 times the speed of the Voyager spacecraft. It is far above the ejection velocity from any normal planet-planet scattering event, which produces only a few kilometers per second of kick. It is also far above the ejection velocity from any normal stellar flyby, which produces at most 15 or 20. The mechanisms we have walked through, the ordinary ones, do not produce planetary escapes from the galaxy. They produce rogues that drift through the galactic disk at modest velocities, making long circular orbits around the galactic center over hundreds of millions of years, but staying in the galaxy. There are, however, mechanisms that can produce escape from the galaxy. They are rare, but they are real, and they put a small fraction of the rogue planet population on trajectories that take them out into intergalactic space. The cleanest mechanism is the one that has been observed in operation for stars. In 1988, the theorist Jack Hills published a paper showing that if a binary star system passes too close to a supermassive black hole, the tidal forces of the black hole can disrupt the binary. One of the two stars ends up captured into a tight orbit around the black hole. The other star is flung outward at extraordinary velocity, sometimes exceeding 1,000 kilometers per second. This mechanism, the Hills mechanism, is now established as the explanation for the population of hypervelocity stars that have been observed leaving the Milky Way at speeds far above the galactic escape velocity. Roughly 20 hypervelocity stars have been confirmed to date. They are all on trajectories that point away from the galactic center, consistent with having been ejected from a close encounter with the Milky Way's central black hole, Sagittarius A star. The same mechanism works for planets. If a planet was bound to one of the two stars in the binary, the disruption that ejects the runaway star can also eject the planet. The planet inherits the high velocity. It leaves the galaxy on a similar trajectory. There are no confirmed observations of a hypervelocity rogue planet. They are far harder to detect than hypervelocity stars, but the theoretical case is unambiguous. The Hills mechanism, operating on planet-bearing binary stars passing near Sagittarius A star, will produce a small, steady flux of planets being ejected from the galaxy on escape trajectories. Over the lifetime of the Milky Way, that flux integrates to a non-negligible population of intergalactic rogues. There are other mechanisms. The most violent supernova explosions, particularly those involving stripped envelope or magnetar progenitors, can deliver enough asymmetric impulse to a surviving outer planet to push it above galactic escape velocity. Some compact object mergers involving recoiling black holes can do the same, although the cross-section for this is small. The cumulative result is that some fraction of the rogue planet population, small, but not zero, ends up moving fast enough to leave the galaxy entirely. Once they are outside the galactic potential well, they are at the mercy of the local group's gravitational landscape and ultimately the Hubble flow. Let us go there. Move the listener to a rogue planet that left its galaxy 10 billion years ago. It is now drifting through intergalactic space, somewhere in the rough vicinity of where the planet started, but well outside the boundary of any galactic disk. Its host galaxy is now a faint spiral in the sky, several million light-years away, visible as a small smudge in one direction. Other galaxies are scattered through the sky in different directions, each one a similar smudge, some larger, some smaller. There are no nearby stars. There are no nearby anything. The space between galaxies is, on a cubic meter basis, almost as close to empty as nature gets. Hydrogen atoms in the warm-hot intergalactic medium average around 10 per cubic meter. In the coldest voids, the density falls below 1 atom per cubic meter. The temperature of the radiation field is the cosmic microwave background, 2.725 Kelvin. The planet has cooled to within a degree or two of that, with its remaining infrared output coming entirely from the slow leak of interior heat. The sky from the surface of an intergalactic rogue planet is the strangest sky in the universe. There is no Milky Way because the planet has left it. There are no nearby stars because there are no stars in intergalactic space. There are only the smudges of distant galaxies hanging in different parts of the sky, each one too far away to resolve individual stars, each one looking like a faint dim cloud. The sky is darker than any sky on any planet within a galaxy could ever be. The sky is darker than the sky at the bottom of an ocean trench on Earth. It is darker than any night you have ever experienced. The planet itself is in equilibrium with the CMB radiation field. The cosmic microwave background photons that have been streaming through the universe since about 380,000 years after the Big Bang are now hitting the planet's surface from every direction, at the same temperature in every direction, at 2.725 Kelvin. The planet's surface, with its interior heat flux slowly leaking outward, settles at a temperature only a couple of degrees warmer than the CMB, maybe 4 Kelvin, maybe 5, cold enough that anything is solid, cold enough that hydrogen itself, the lightest of all elements, is at the edge of becoming a solid or a superfluid liquid at certain pressures. The interior, though, is still warm. Even 10 billion years after the planet was ejected, the long half-lives of uranium and thorium and potassium-40 have only delivered a fraction of their total energy budget. There is still radiogenic heat being produced in the core. The mantle is still convecting, slowly, on geological timescales. If the planet had a subsurface ocean before ejection, that ocean is, in some scenarios, still liquid. The ice cap above it is now much thicker than it was maybe 50 kilometers thick, instead of a few, but it is still insulating. The interior heat is still being trapped below it. There is still a liquid layer. If there is anything alive in that liquid layer, it has been alive in the dark for 10 billion years. It has no concept of where it is. It has no concept of when it is. There is no event in its environment that could possibly distinguish the moment its planet was ejected from the moment 10 billion years later. The vents at the ocean floor have not changed. The chemistry has not changed. The temperature has not changed. The proton gradients across the mineral barriers are the same gradients they were when the host galaxy was bright in the sky outside. The biosphere, if there is one, lives in an environment of complete temporal flatness. Nothing in its world ever marks the passage of cosmic time. That is, in some ways, the loneliest version of the rogue planet story. Not because there is nobody there may be something alive, by the most cautious estimates of habitability, but because there is no possible signal that could ever cross the gap between that world and any other. No telescope ever built, or that could be built, would detect an intergalactic rogue at any reasonable distance. The infrared output from a planet at 5 Kelvin, at a distance of millions of light years, is below the noise floor of any instrument we can imagine. The planet is, for all practical purposes, invisible. It will always be invisible. If there is anything aware of being on it, that awareness will not propagate. The numbers, again, run unsettlingly large. If the Hills mechanism, plus the supernova mechanism, plus any other minor channel, produces even a small fraction of all galactic rogues at velocities above the galactic escape velocity, the integrated intergalactic rogue population over cosmic time is enormous. Trillions of planets, possibly, scattered through the local group and beyond, drifting toward the Hubble flow at the slow speeds of their original galactic kicks. Most of them are dead worlds, frozen solid, no subsurface ocean, no liquid layer, no life. But the math does not rule out the warmer ones. Some of them have subsurface oceans. Some of those oceans may have biospheres. None of those biospheres will ever be known about by anyone, by anything, ever. There is a quiet that goes with that thought. It is not a fearful quiet. It is the quiet of recognizing that the universe is so large that even after physics gives life every chance it can, the chances will play out in places that will never communicate with each other. Most of what happens in the cosmos happens alone. Most of what is alive, if anything is alive in the dark places, is alone. The lit places, where civilizations can rise and astronomers can sweep the sky and discover their universe in detail, those places are extraordinarily rare. They are the local exception. The default is the silent dark, with whatever warmth and chemistry it happens to hold, going about its business, undisturbed and unwitnessed, for billions of years. That is the bottom of the picture. There is one more thing to say about it, and then we will close. The closing returns to the surface, back to the kind of world the listener is currently sitting on. Part 12. The closing reframe. Step back, for a moment, from the dark places. From the freeze and the subsurface ocean and the intergalactic void, come back to where you are. Wherever you are listening from, there is, almost certainly, a star nearby. There may be sunlight outside your window, or there may have been earlier today. There is an atmosphere over your head, breathable and warm. There is liquid water on the surface of the planet you are on, in vast quantities, distributed across continents and oceans and rivers and lakes. There is weather. There is, in some directions of the sky, the rising and setting of a yellow star that has been the central fact of every day of your life and of every day in the lives of every human who has ever existed, and of every organism that has ever evolved on this world. That arrangement is the only arrangement you have ever known. What the rogue planet category invites you to do is recognize, slowly and without urgency, that this arrangement is not the default arrangement in the universe. It is the local exception. The galaxy contains a few 100 billion stars. The galaxy contains, by the current best estimates, somewhere in the same range or substantially more starless planets. Most of those starless planets are smaller than the planet you are on. Most of them are frozen solid on the surface. Some of them, possibly many of them, have liquid water under their ice. Some of those, possibly, have something alive in that water. None of them have a sky like yours. The typical planet in the universe, the one that statistics now suggest is the most common kind of world out there, is a planet that has never seen a sunrise. There is no warmth from above. There is no day. There is no night. In the human sense, only the unchanging dark sky with the slow shifting of the galaxy in one part of it. The surface is cold past the freezing point of nitrogen. The atmosphere is on the ground. The oceans are solid all the way down, or solid most of the way down, with a thin liquid layer at the deepest interface where the planet's own interior heat is still leaking out. That is the median world. That is the median experience of being a planet in the cosmos. We are the lit exception. The bright pinpricks of light you see when you look up at the night sky are not a representative sample of what is out there. They are a tiny minority. They are the few 100 billion places where a planetary mass body has, against the statistical odds, ended up arranged in a stable orbit around a still-burning star. The vast hidden majority, the population that probably outnumbers the visible stars by a factor of a few or many, is in the dark. The dark is the rule. The light is the exception. You are sitting in the exception. That is the small adjustment the rogue planet category asks you to make. It is not a dramatic adjustment. It does not change how Wednesday morning works. It does not change whether tomorrow's sunrise comes. But it changes where you imagine yourself standing in the cosmos. It moves the center of gravity of your mental picture of the universe away from the lit places and toward the dark places. The lit places are still there. They still matter. They are still the places where civilizations like ours can exist and ask questions like the one this video has been about. But they are no longer the bulk. The bulk is somewhere else. The bulk is invisible. There is a peculiar kind of comfort in that thought, if you let it sit. The universe is enormous. It is enormous enough that the typical experience of being a planet is one of isolation, in a thermal sense and an optical sense and a communicative sense. Most worlds will never know they exist. Most worlds, whatever is happening on or in them, are happening alone. The fact that we know this, the fact that, on a single warm planet in the lit minority, organisms evolved with the capacity to look up at the sky, infer the existence of bodies they cannot see, count them, model them, and write down that the cosmos is mostly dark, is itself a strange privilege. We are in a position to know the structure of the universe. Most planets are not. So when you look up at the night sky tonight, if you can see the night sky from where you are, look at the bright pinpricks. Then look at the spaces between them. The spaces are not empty. They contain, by the best current count, more planets than the pinpricks themselves do. Each of those planets is a small dark sphere drifting through interstellar space. Each one has its own slow trajectory through the galaxy. Each one has its own interior heat, its own composition, its own thermal history. A few of them, in the cautious estimates, may have warm subsurface oceans under their ice caps. A few of those oceans, in the most optimistic estimates, may have chemistry running in them that we would call alive. You will not see any of them. They will not flicker. They will not appear on any photograph of the night sky that you ever look at, because they are too dim and too cold to register on any instrument we have built. But they are there. They are the silent majority. The starless worlds are the cosmos's default condition, and they have been the default for as long as planets have existed. The lit arrangement is the rare one. The flicker is the proof. The ember beneath the ice is the optimism. The warm in the dark is, on a galactic scale, where most of the chemistry of the universe happens. It is where most of the slow story of the cosmos is being told, in places that nobody will ever visit and that nobody outside them will ever know. Tomorrow morning, if your planet's rotation brings the sun back around to your part of the sky, take a moment to notice it. The warmth on your face is not a normal feature of being a planet. It is a special feature of being on this one. Most planets do not have it. Most planets have not had it for billions of years. The sky above you is, statistically speaking, a strange sky. The sun, rising over the horizon, is, statistically speaking, a strange event. The fact that you exist, on a lit world, in an arrangement that the universe has produced only rarely, is one of the quieter and stranger facts about your address in the cosmos. A planet that never sees a sunrise is the typical planet. You are sitting on the exception. And that exception, against the silent dark majority of worlds, is exactly where you happen to be. That is the picture. There is no urgency in it. There is no warning. There is only the slow recognition that the universe's typical condition is darker, quieter, colder, and stranger than the textbook picture allowed for. And there is, somewhere in that recognition, a small steady warmth. The warmth of knowing that you are in the rare arrangement. The warmth of being, for these brief decades, in one of the lit places. The dark places will go on as they always have. The vents at the bottoms of the subsurface oceans will keep pushing mineral-rich water into the cold. The interior heat will keep leaking outward, slowly, on its long radioactive half-life. The rogue planets will keep drifting through the galactic disk and out into the intergalactic void, with no surface story to tell, with their internal stories sealed beneath kilometers of ice. The cosmos will keep being, at scale, mostly dark. And you will keep being, at the small scale of your life, on a planet with a sky. The loneliest planet in the universe is somewhere out there, in the void between galaxies, drifting through nothing, toward nothing, with no signal that could ever cross the gap to anywhere else. It does not know it is the loneliest planet. It does not know it is a planet. It just is, warm at its core, cold at its skin, alone, and waiting, in the way that things in the dark wait, for nothing in particular on a timescale that has no edge. That is the picture. We can sit with it now, for as long as the night allows.